Well, good morning, everybody. Thank you for joining us today for our webinar on analyzing bubble characteristic simulations of fluidized beds. Today we have, this is a joint webinar between CPFD and Tecplot, so I'm excited to have our partners and friends from CPFD software with us today. Our presenters are Sam Clark. He is the product manager for Barracuda Virtual Reactor at CPFD. And myself. My name is Scott Fowler. I'm the product manager for Tecplot 360, and you'll see a demo today of Tecplot 360 and Tecplot for Barracuda, which is the free version of Tecplot 360 that comes with Barracuda Virtual Reactor. Today, we're going to give a brief introduction to Tecplot and CPFD. Some of you may come from the CPFD side of things and want to learn something about Tecplot. Some of you might be coming from the Tecplot side of things and want to learn something about CPFD. So a brief introduction to both companies. Sam is going to give an introduction to fluidized bed systems. So he has a great presentation there, and he'll be talking about bubble characteristics and some experimental techniques and looking at the simulation results. And then I'm going to be presenting how we helped CPFD analyze bubbles in the use cases, because there are some shortcomings to some of these experimental techniques. And then, of course, open for questions and answers at the end. Okay, so really quickly, who is Tecplot? Well, we were founded in 1981 by a couple of Boeing engineers who were writing CFD codes themselves, and at the time there was really nothing on the market to visualize the CFD results. So they hired an engineer who's still at Tecplot today to start writing Tecplot software. Now, in that time, we've amassed about 47,000 customers worldwide. People widely regard us as the most complete desktop solution for post-processing software with our integrated line plotting, 2D plotting, 3D plotting, and even polar plotting. And we're dedicated to saving engineers time. So how do we save you time? Well, we do that in three primary ways. One is solving the big problems with very large data. So we've developed a new file format called Sizzle, or Subzone Load on Demand, which allows you to load just the cells you need for the attributes through the plot. So you can see that representation here. We have a large block of data. Most post-processors require that you load the entire block just to create that little slice. Well, the Sizzle format allows you to load just the cells around that slice, which saves you time, saves you RAM. The next point is we have a product called Tecplot Chorus that comes with a full version of Tecplot 360, and this piece of software is designed to help you with designs of experiments, to help you with aerodynamic databases, so you can really get a nice overview of all of your simulated results in one view. And this also allows you to dive into each one of those cases in Tecplot 360 for further investigation of your data. And then finally, automation. So Tecplot 360 has a really rich macro language, and it also has a very nice Python language. And you'll be seeing some of the Python language today. And this allows you to automate your workflow so you spend less time pointing and clicking in the user interface, and you can get your answers faster. So with that, Sam, do you want to give us an introduction to CPFD?
Certainly. The team here at CPFD has expertise in fluid particle systems and specifically simulating these systems with our software product that's called Barracuda Virtual Reactor. Our software is designed to simulate the flow behavior of particles and fluids, either gases or liquids, in chemical reactors, and we account for the thermal and chemistry aspects of these systems to accurately predict three-dimensional and time-varying system behavior. People use Virtual Reactor to troubleshoot existing systems or to test out ideas for improving reactor performance, and also when they're designing new systems and processes. We deploy Virtual Reactor through software licensing, engineering support, and simulation services. Before we jump into the analysis of bubble characteristics, I'll give a brief introduction to fluidized bed systems in case anyone joining the webinar today isn't familiar with them. A fluidized bed is a vessel containing particles, which we call the bed, and a fluid, either a gas or a liquid, is introduced at the bottom of the bed. Shown here is a video of an experimental fluidized bed that was designed to be thin for easy visualization of the bubbling behavior. At very low fluid velocities, the particles won't move as the fluid passes through the interstitial spaces between the particles. But as the fluid velocity is increased, there comes a point at which the drag of the fluid on the particles will cause the bed to expand. The particles will start to move, and at this point we say that the bed is fluidized. When the bed is fluidized, the mixture of particles and fluid will behave like a high density fluid, which has led to many useful applications in a number of industries. A number of important chemical processes involve reactions between particles and gas, and fluidized beds are used in things like chemical production, petrochemical processing, power production, and many other industries. The animation on this slide shows the particle flow behavior from a simulation of a fluidized catalytic cracking or FCC regenerator. These systems are often 10 meters in diameter and 20 or more meters tall. So even though we'll be focusing on a small system in today's webinar for the sake of demonstrating post-processing concepts, keep in mind that many fluidized bed reactors are very large when used for industrial processes. Using fluidized beds as chemical reactors offers a number of advantages. One is that temperature distribution within a fluidized bed is often quite uniform because the particles have such a large thermal mass and the gas and particles in the bed are well mixed by the fluidization process. Another advantage is that because the particles are fluidized, they can flow like a fluid from one vessel to another, and this allows engineers to design continuously running processes as opposed to batch processes. FCC regenerators, like the one shown here, for example, have particles continuously flowing into and out of them, and they're just one component of an overall looping system that is usually intended to be run for 3 to 5 years without interruption. Since today's webinar is about analyzing bubble characteristics, I want to make sure it's clear what we mean by the word bubbles in fluidized beds. The animation shown here is a thin gas solid fluidized bed, and this is the example system that we'll be using for the live demo portion of the webinar a little bit later. The particles have been colored by volume fraction, which is how densely packed they are relative to each other. Red regions have particles that are densely packed together, while the green or the blue regions have more dilute particle loading. We call the regions of relatively low particle loading bubbles. As we watch this animation, we can see that the bubbles start out small near the bottom of the bed. They grow larger and coalesce with each other as they rise in the bed, and their rise velocities increase as their sizes increase. Bubble characteristics such as size and rise velocity are highly dependent on particle size and density, gas velocity, how gas is fed into the bed, and the operating conditions of the fluidized bed, such as pressure and temperature. Engineers designing and troubleshooting fluidized beds care about bubble characteristics because they can have a significant impact on unit performance. Small bubbles have much more surface area for the gas to contact the particle phase, and this can often lead to faster chemical reaction rates and better system performance. And if the bubbles get too large, the unit can start experiencing large pressure fluctuations and even structural vibrations in some cases. Scientists and engineers have developed many experimental methods for measuring the characteristics of bubbles in fluidized beds. This table lists a number of well-known intrusive and non-intrusive methods, but it's by no means a comprehensive list. Each method has strengths as well as shortcomings. The intrusive methods shown in the left column of the table usually involve placing instrumentation inside the fluidized bed. This has the potential to change the flow behavior, and the degree of intrusiveness varies from one method to another. The non-intrusive methods shown in the right column of the table are designed to measure bed characteristics without changing the flow behavior, and these often use special instrumentation surrounding the bed to collect data either visually or electromagnetically. We'll briefly discuss a few of these measurement techniques in the next slides. The first method we'll talk about is digital image analysis. This is a process that uses images captured during the operation of a system, which are then analyzed to determine properties such as bubble size or rise velocity. The diagram on the top right illustrates a typical setup for digital image analysis used in conjunction with a research scale fluidized bed. A camera takes numerous pictures of the bed, which are then transferred to a computer for post-processing. The images are analyzed algorithmically by scripts, and you can see an example of how an algorithm could parse the images for this system on the bottom right. There are several advantages to this technique. Foremost, it's a non-intrusive technique, meaning that it will not interfere in any way with the flow behavior of the system. Additionally, it can be very precise given that appropriately high-end equipment is used. However, digital image analysis is severely limited in that it is mainly useful for two-dimensional systems, and the vessel walls must be transparent in order to see the bubbles. So this restricts its application primarily to academic fields with limited practical use in industry. Another method for measuring bed properties is called optical probes. This method has been in use since 1958 and operates by optic probes sending light into the dense phase of a fluidized bed. Depending on the configuration of the probes, either the reflection or the transmission of the light is measured by another optical probe in the system. The magnitude of the reading is used to measure voidage or bubble size in the bed. You can see on the right an example of how these probes look in a real-life system, as well as a diagram on the bottom right that demonstrates the transmission-reflection relationship that the method uses. Optical probes are capable of giving very detailed measurements local to the positions at which they are mounted, and they're a well-established technology that can provide a low-cost solution in many projects where people need to measure bubble properties. However, these probes are inherently intrusive, and they'll always introduce some amount of disturbance to the flow in the system. Additionally, the probes can be sensitive to harsh conditions such as high temperatures and pressures that are typical in chemical reactors. A lot of these shortcomings have been researched and mitigated over the years. For example, the probes in this picture are quite small and designed to minimize the intrusiveness within the bed. The final method we'll discuss is a relatively newer approach, which was first conceptualized in 2003, called electrical capacitance volume tomography, or ECVT. This method uses capacitance sensors distributed three-dimensionally around a fluidized bed, as illustrated in the upper right image, and it takes high-frequency measurements to sense variations in the electric field of the bed. These readings allow for construction of 3D images of the bed through time. Like digital image analysis, ECVT is a non-intrusive method. It is also a holistic method, meaning that the analysis of ECVT readings can take into account the entire 3D system encompassed by the capacitance sensors, as opposed to a collection of just 2D snapshots, which you would get from digital image analysis. Compared to other holistic methods, ECVT is also cheaper, safer, and more flexible to different system geometries. However, it is inherently limited in the spatial resolution due to the mathematical formulas used to recreate the bed, and some other holistic methods are capable of producing more accurate results for certain bed characteristics. The topic of measuring bubble characteristics experimentally has been researched extensively over the years. Here's a list of the published papers we referenced in just the last 4 slides. So there's a lot out there. If you're interested in looking into any of these methods in more detail, definitely recommend starting with some of these resources, and there's a lot of research out there available to look at. Getting back to the world of simulations of fluidized beds, there are a number of techniques that people use for analyzing simulation results in order to compare with experimentally determined bubble characteristics. The most common approach, at least in my experience working with users of Barracuda Virtual Reactor, has been digital image analysis of exported frames, such as the one shown here on the right. This is directly analogous to the experimental image analysis technique discussed earlier and requires users to write custom scripts that perform the image analysis. Another approach is to use high-frequency pressure or volume fraction data from the simulation results to mimic other experimental methods. For example, you could use 2 closely spaced volume fraction measurement locations in a simulation, and you can get data that's analogous to optical probes. Another approach is to write very low-level custom scripts or programs to perform the analysis of the data. With these types of scripts, you can identify bubbles algorithmically and calculate characteristics of interest. However, these are very challenging scripts to write. So when I hand it back over to Scott in a moment, he'll demonstrate some newly introduced capabilities in Tecplot that allow bubbles to be identified and analyzed in a very flexible manner. And the process is much more straightforward and easier than what would have previously been required for writing your own custom scripts to perform all of these low-level bubble identification steps. So Scott, I'll pass the presentation back over to you now, and you can show us how Tecplot 360 can help in this problem.
All right. Well, so today I want to start with Barracuda Virtual Reactor and take you from start to finish with this workflow of using Tecplot for Barracuda and Tecplot 360 for dealing with these fluidized beds and analyzing bubble characteristics. So let's just start right from Barracuda Virtual Reactor. You can see that they've created a nice post-processing menu option in the tool, and you can launch Tecplot directly. So again, this is the free version of Tecplot 360 that comes with Barracuda Virtual Reactor. And for those of you that may be coming from the Tecplot side of things, you'll see, well, what's different between this and Tecplot 360? Well, CPFD has done a great job of adding some quick shortcuts in the Tecplot quick macro panel to come up with some default views, and they've also written a custom data loader that is available on the file menu, load Barracuda data. So we'll start from there. I'm going to load a 3D data set, and I have 100 time steps of this data set, but for the demonstration purposes, we'll just load the most recent time step from this simulation. So click load 3D data set, navigate to our folder, and we can select any one of these files, and the Barracuda loader will know which data to load. So pretty nice user experience there. All right, so we have our data set loaded. Sam was talking about bubbles being identified by particle volume fraction. So over here on the quick macro panel, I'll just double click, or you can single click and hit play, and that'll show particle volume fraction. You can see that this is, like Sam said, this is a pretty thin sheet of data, right? Like in the image analysis case, you do need it to be fairly thin, so that's kind of simulated here. We'll just snap to a quick view. Let's turn off translucency and lighting effects so we can more accurately see these bubbles. So what we want to do here, our goal here, is to quantify the volume of each one of these bubbles. Well, the problem is that Tecplot 360 needs each one of these bubbles to be a separate zone. And so I like to think of Tecplot itself as being like, like Legos. We have a lot of Lego bricks that you can use to develop a workflow. In coming up with this webinar, Sam and I were talking about Tecplot, and it's like there's no bubble analysis button. So we're like, man, it's like Legos, right? You can use the value blanking feature, the extract blank zone feature, the integration feature, and you can chain all of these together, and you can build a tool like you would build a Lego model. So I'll use that analogy a bit today. So the number one thing in using Tecplot for any analysis is kind of knowing the set of features or the set of Lego bricks, the shapes that you have available to you. And as a new user, that can be hard. And that's one of the great things about having access to our technical support staff. You can find out what features are available. So let's start with the end in mind. And we know that we want to integrate the volume of each one of these bubbles. So we do have this dialog in here, integrate volume, but this relies on each one of these bubbles being a separate zone or a separate block of data. And this is just one big block of data right now. So let me explain that. If we go into the dataset information dialog, and we'll go into the zone style dialog, you can see what we're showing right now is the cell data. And this is just one big block. So we need to figure out a way to separate each one of these bubbles into its own little block of data. And we'll do that in a number of ways. So let's start with our value blanking tool. And what this allows you to do is it allows you to apply thresholds to your data to isolate cells that you want to see. So if I turn on the mesh, we can see a fairly coarse grid here. And we can see that the bubbles are identified by particle volume fraction. And so we'll use the probe tool to find out where that threshold is. So that brings up the probe dialog here. And we look at particle volume fraction, it's about 0.24. So let's use the value blanking capability to blank based on particle volume fraction. And I want to remove cells that are greater than 0.24. We'll activate the value blanking. I think that was a little too much. So this is a little bit of art, a little bit of science. So let's go with 0.3. And you can see that we've been left with the cells above the bed here, and we want to eliminate those as well. So we know that a nice criteria here is to remove these where the pressure is a lower value. And so we'll again probe up here, and we can look at the pressure variable. You see it says not loaded, and so this is an interesting thing to know about Tecplot 360 and Tecplot for Barracuda is we actually won't load the data until you actually need it. So this saves RAM, it saves time because we're not loading that data off disk, but here I actually need it. So I'll say load variables, I'll select pressure and hit load. Now you can see the value here. So where I probed is this value. So let's add another blanking constraint when pressure is less than 1004. You can see I didn't quite blank enough. So again, a little bit of art, a little bit of science, but we found pretty good values to represent that data. Okay, so now I have these value blanking constraints set that we're only left with the cells that actually represent the bubbles. So Tecplot has a couple more capabilities that will allow you to split these into their individual components. So we'll now go to data, extract, and we'll say extract blanked zones. So what this is going to do is it's going to take this cell data and it's going to create a new zone or a new block of data that represents just this set of cells. So if I go into now the dataset information dialog and scroll down to the bottom, you can see that I have this new zone called extracted cells, but now this represents all of these cells in one big block. And again, going back to that perform integration dialog, that would, if we computed the volume, it would compute the total volume of all of these combined rather than each individual one. So this is where it became really interesting. When Sam and CPFD said, hey, we want to analyze these bubbles, we're like, oh man, we have this ability to do this extract blank zone and isolate the bubbles, but we don't have a way to isolate them individually. So this is where we had to go back to the Lego factory and build a new brick. What we did is we came up with a new capability called extract connected regions, and we don't actually have it available in the user interface yet, but we do have it available as part of our macro and scripting language. So sometimes that Lego brick can be a little bit hard to find, so you might have to look at our documentation. So let's go into the scripting guide or run a script here, and let me just show you what this script in Notepad++, you can see that we have effectively a two-line script that prompts you for the zone that you want to split, and then it calls this function called extract connected regions using that source zone. And what this is going to do is it's going to split that data into its commensurate parts or its individual set of zones. So we'll hit open. And if we bring up the dataset information dialog, and you can see a little visual here where we have these orange boxes that surround each one of these, and now we have one zone per bubble. So if I were to go into here and say just show one of these, we have just one bubble here. Now you can't actually see it because this is volume data, and by default Tecplot doesn't show the outer boundaries of volumes. So we'll say show the boundary cell faces, and now you can see the cells that are associated with that bubble. Okay, so now we're nearly there. Let's just select all of these and turn them on. Boundary cell faces. And if we go into perform integration, we can now do length, area, volume. So because these are three-dimensional cells, it's going to compute the volume. If it was two-dimensional cells, it would compute the area, and if it was 1D, then it would compute the length. And we will select that set of zones that we just extracted. And I'm going to just show the tabulated results. So this does the integration, and you can see that we have these tabulated results now, which express the volume for each one of these. Well, really, we want to get this data back onto the zones so that we can visualize it in place, right? What I really want to do is I want to color each one of these bubbles by its volume. And so here again is where we're going to use our Python API, because we don't quite have that capability built into the product. So again, we're doing a custom analysis here, and we're going to use the Python layer to do that. We're going to, let me just show you the Python script now that we wrote to do this, and you'll see a lot of commonality between what we did in the user interface and what we did in Python. And yes, Sam mentioned that you have to, for other bubble analysis, you have to write long custom scripts. And yes, this is a custom script, but I hope that you'll find that it's fairly easy to follow. And the way we've written this script is it's going to take a Tecplot layout file. So that would be a file which represents this state as the input, and it's going to create a new data file with the individual bubbles as an output. Okay, we'll start from the beginning here. So we've written a script to use a module in Python called argparser, so we can take some input values. You can see that we wrote a little custom function to use that integrate command, and so just easier to call a small function. We're opening the Tecplot layout file that we've defined, and we get a hold of the set of zones that represent the cells. So this could be used for a transient data set as well. This will work equally well for a long transient data set. We make that call to extract blanked zones. So again, this is assuming that you have set up the value blanking constraints in the layout file, and it will do that extraction. And then it will loop over each one of those time steps or each one of those extracted zones. And you can see down here a few lines on line 45 that it will extract each one of those to the connected regions. Once we have each one of those zones, it will again loop over those and do the integration, integrate the volume for each one. And then finally, once we have that integrated volume result, we're going to, using Tecplot's equation processing, put that value back onto the volume data. So then we can plot it in place. Okay, so to execute this command, we're going to use scripting, Python scripts. In order to run with Tecplot 360, we need to allow Python connections. So we'll launch this Python connections dialog and turn that on. And that will allow an external script to be able to communicate with Tecplot 360. So we'll just run this script. You can see that I'm running Python-O, so that runs in optimized mode, so it's going to run faster. We're going to run our Python script using a layout file that I've produced as an input. We're defining the output with the bubbles file, and then we're going to say -- connect. This was engineered into the script, so it will actually connect to this version of TechPlot 360. So just hit enter. You can see that it's connected. It loaded the layout, so that was a little flicker of the change of style there, and now it's extracting the blank zones, extracting the connected regions, and then it's going through and doing the integrations. And this will just take a couple of seconds to run. And I will make a note here that running Python is going to be faster in batch mode versus connected mode. The way our connected Python works is it communicates via the Python language and TechPlot 360 using sockets. If you have the full version of TechPlot 360, you can run this entirely in batch, and that will run very, very quickly. So if we look at, so I have another version of the script here, put on the command line. So this is going to load all of my time steps and create a file called PLT. You notice I don't have the -- connect. So this is going to run fully in batch mode, and this takes about 45 seconds to a minute to run through all 100 time steps, whereas just one time step took about 20 seconds. So big advantage of being able to run in batch. And again, that's what you need. You need a full version of TechPlot 360 to get the batch mode. So that'll just run in the background. And while that's running, we can finish our analysis here. So again, if we go into the dataset information dialog, we can see that we have a new variable here called volume, and we have the same values that we saw earlier in the perform integration step, and we can color these by our volume as well. Now, you may go, well, those look like they're all constant. They are, because we're actually looking at both our cells and our extracted regions. So let's turn off the cells and turn on the boundary cell faces. There we go. And so now we can see that these are actually colored by the volume. So I hope that gives you an idea of how you can use TechPlot 360 and TechPlot for Barracuda to analyze bubble characteristics. Again, like I said, I like this Lego analogy. You know, TechPlot has a lot of building blocks to it. Some of the building blocks are more obvious than others. And so it's nice that you can have access to our tech support group to help you figure some of that out. So with that, I'll pass it back to Sam, and we'll finish up the webinar here.
Great, thanks, Scott. So here, hopefully people can see my screen again. If you have any questions about the information that Scott just presented, please put those into the questions panel, and we'll get to those in just a moment. We also wanted to let you know about a number of upcoming events for both CPFD and TechPlot. Please visit our websites for more details, where you can usually find registration links for each event, depending on what kind of event they are. In the month of October, CPFD will be participating in an AWS Europe, Middle East, and Africa Manufacturing and Industrial Symposium, and Peter Blazer will be speaking there. TechPlot is also releasing a new version, and I'll let Scott speak to that in a moment. They'll have a webinar for that. CPFD also has a joint webinar with NVIDIA and Mark III Systems coming up about running Barracuda in multi-GPU mode on NVIDIA's latest and greatest DGX Station A100. And Barracuda Virtual Reactor is a Sustainability Award finalist for the Hydrocarbon Processing Awards this year. So that award ceremony will be at the end of October. And then our next new user training class for Barracuda is scheduled for November 1st through 5th. And so if anyone on the webinar today is getting started with Barracuda and wants more information about that upcoming training class, please contact us, and we'd be happy to talk to you about that. Scott, anything you wanted to add on the TechPlot webinar and release?
Yeah, just that we do have a release coming up. It will be available October 20th, and we're doing a webinar that day. There are some interesting new features. We have some performance improvements. We have some updates to contour legends and our equation processing and how we deal with transient data. So it should be a pretty good webinar, and we'll also give a little bit of a sneak peek onto what's coming in 2022. So please do come and watch that webinar.
Great. Yeah. So at this point, I see a number of questions coming in. The first question I see is, if you calculate the total bubble volume using volume fraction, what would be the error relative to this method? In this case, I think the crux of this question is probably related to your grid resolution. So in this case, as Scott pointed out, the grid was relatively coarse. We wanted something that would run fast and would be easy for the purpose of illustration. But I think probably the limiter on your accuracy could be your cell size. And so just keep that in mind when we're looking at this volume fraction data. Each cell in the Barracuda simulation has a single value for the particle volume fraction at any given point in time. So that's probably really where your resolution will be limited. Let's see, next question, would it be possible to map a Z location onto the bubbles? Oftentimes it's nice to see how the bubbles grow versus height. And so, yeah, I think that should be very possible. I mean, I'm only kind of a newbie myself when it comes to PyTecplot scripting, but Scott, can you speak to that? Would that be pretty easy to grab kind of the average Z location on each bubble and record that as well?
Yeah, certainly. Yeah, what I showed you there was just computing the volume, but that integrate panel also has the ability to compute averages. So a version of the script that Sam and I worked on earlier also computed average velocities. So you could see the velocity of the bubbles. And Sam also took it a step further to put in an algorithm for computing a diameter of those bubbles. You saw that some of them were oblong, so not exactly circular, but you can make some assumptions about bubble shape. So yeah, lots of flexibility in there, certainly.
Yeah, I see a couple questions here related to getting this script that Scott demonstrated and also maybe preparing kind of a concise documentation of how this is done. So just for the Barracuda Virtual Reactor users on this webinar, we will definitely do this, right? I will create a support site post where we show in a concise number of steps how to do this, and on that post we can definitely share the script and make it easy for people to access that, so you don't have to watch the full webinar recording every time that you want to try to do this. Let's see, other questions. Do you see any other questions on there that?
Yeah, there's do we have to create a 2D slice first to analyze bubble volumes with Tecplot? And the answer is no. So in this one, we used the full volume cells for analyzing the bubble volumes. So you know, if you wanted to create a 2D slice first, you could. But yeah, in this case, we definitely did it with the full volume cells.
Right, and maybe to add a little bit to that as well, for most virtual reactor users, really you're probably modeling big three-dimensional systems that are, you know, like I said in the earlier part of the presentation, maybe 10 meters in diameter, 20 meters tall. So for the most part, people are probably going to be interested in bubbles that are inside the bed, and they'd probably be interested in the three-dimensional diameter or volume. So yeah, that's totally possible, and kind of using the method that Scott showed here, you would get that three-dimensional volume that the bubble occupies within the 3D space, and not just, you know, not just like this example that was kind of 2D for the sake of illustration. Let's see. Another thing, I see a question here. Why did the volume why did the particle volume fraction range from like 0 to 0.5 versus 0 to 1. And so this is just kind of a fundamental behavior of the way that particles pack. Most particles can only pack up to a fraction of about 0.6, and there's always some gas space in between. And so that's why even the highest red color on our volume fraction scale was probably around 0.6, rather than going all the way up to 1, which would indicate like a solid block of particles with no gas in between. Another question, can you make more than one variable per bubble at the same time? And if so, could you plot bubble velocity as a function of bubble size? And so, yeah, you can definitely do this. And this is kind of similar to the previous question about maybe attaching the Z position or the elevation of the bubbles. So yeah, whatever information you're interested in can generally be calculated through that PyTecplot script. So yeah, if you wanted bubble velocity, bubble size, bubble Z position, all of those sorts of things are possible to extract.
Yeah, and I think it's also important to note that you know, even custom values, you know, like Tecplot doesn't have the ability to built in to compute the diameter of a bubble. So, you know, Sam, there's a heuristic that you came up with for determining what that diameter was, and so in your version of the script, you had added that capability. So, you know, if it's kind of, you know, if you can imagine it, you can do it pretty much.
Yes. Yeah.
So the Python layer really opens up you know, really has opened up Tecplot 360 from being just a visualization tool to an analysis tool. And so that connection with, you know, being able to access your raw data with Python really opens up a lot of interesting workflows such as this one.
Definitely. I see one question here. How do people get the add-on to separate the blanked regions as separate zones? And I believe this came out in a specific version of Tecplot, and I know the Barracuda version that you need, at least, that includes that version. So if you want this capability, you need to upgrade to Barracuda version 21.0.1, which we released last month, and it includes this capability to extract blank zones or extract connected regions. And Scott, am I off here? I thought it was like 2020 R2 on the Tecplot version.
Yeah, that's right. The extract connected regions capability was introduced as a macro function and Python function in Tecplot 360 2020 R2. We have not made it available to the user interface yet, but it is available in the scripting language since then.
Great. Scanning through this list here still, do you see any others, Scott, that you'd like to speak to?
Let's see.
You can make my window bigger.
There's the most recent one is what is the maximum number of clusters or smallest size of particles that we can do corresponding simulation by Barracuda?
Okay, yeah. And then also, what are the heating mechanisms in Barracuda? So this is not necessarily Tecplot questions, but just kind of practical Barracuda capability question. So in general, people model very, very large systems with Barracuda. There's no limit on the number of real particles that you can model. Essentially, Barracuda models particles as clouds of particles, so it kind of groups them for the sake of the numerical method. And right now, with kind of the latest GPU cards and the latest computers, people are running Barracuda models that might have something like 20 million to 30 million clouds is probably a common number. We've run simulations up to like 100 million clouds, but typically you would need a system with a lot of memory, RAM, and large GPU cards to do that. So I would say something like 20 to 30 million clouds is not uncommon these days. And then the smallest size of particles, again, there's no inherent limitation in the code, but most people are doing something like particles in the range of maybe 10 micron diameter to 1,000 micron diameter. That's kind of the most common range of particle sizes that people tend to be simulating. And then heating mechanisms implemented in Barracuda. We have conduction and convection between the particle phase and the gas phase, and then between the gas phase and any thermal walls. And then we also have some radiation models. If you're running systems at very high temperature or with particles that are a very different temperature than the surrounding fluid, those radiation models can be implemented or can be enabled in the software.
Yeah, and I'll just make a point about post-processing with that, that many particles. So anything over in TechPlot, we found that at least on, kind of consumer grade hardware, I'm running on a laptop. You clearly saw that it struggled a little bit today with GoToMeeting, which was odd. But we see that anywhere in like the 1 to 5 million particles tends to start taxing the graphics card, especially if you're using spheres as a way of representing those particles. So we recommend using the point representation, especially when you have that many particles. Sam, I believe Tecplot for Barracuda, you do that by default with some of those quick macros, isn't that right?
Yes, exactly. Just for the purpose of quickly analyzing the results and getting those engineering conclusions, we by default render all of the clouds or particles as points. And then if you want to make a really awesome looking animation and you can afford the extra processing time, you can render them as spheres. But most of our analysis is done in the points view.
Right.
Okay, I don't think I see any other questions coming through. So I think we've covered.
Yeah, I think we've covered it.
Great.
Well, Sam, thank you for your awesome presentation today. I appreciate the expertise and appreciate the partnership with CPFD, and I hope that for your customers and my customers that we've all learned something today. And if you have any questions, please do feel free to email either of us. We're here to help.
Yeah, and thank you, Scott. We appreciate the collaboration as well. So I'll go ahead and end the webinar at this point.